Hello everybody, this is Ahmed Hameda, Professor of Thermodynamics in GR 130 for this summer B 2020. So today's lecture, we're going to summarize, repeat everything we did in lecture 1, just summarize it, concise it in just about 30 minutes for you. So what we're going to take today is definition of thermodynamics. What thermodynamics is? Thermodynamics is two words, thermodynamics. Thermo means temperature, dynamics means flow, change. Something happened in our system. These are the two keywords when you hear thermodynamics supposed to flash in your mind. So today's lecture, we're going to divide it into 5 sections. So section 1, we're going to take a brief introduction. 1.2, talk about units and dimensions. Section C, we talk about systems. Section 1.4, we talk about properties, what its properties are. 1.5, we talk about density and specific volume. This is our lecture today. Okay, so for introduction, what thermodynamics is? Any system that has temperature, has energy, has work, it's a thermodynamics problem. Oven, microwave, even light, fan, engine, jet engine, all of these are thermodynamics problem that we're going to cover in this course. A lot of application. Thermodynamics is the science of energy and entropy. Entropy means disorder. So we will have a lot of systems that we have energy from heat to work or work to heat, and we have entropy. We have losses. We have problems in our system. So thermodynamics, science of energy and entropy. We're gonna have the first law of thermodynamics, which is energy can be neither created nor destroyed, but it can transform from one form to another. So energy only transform from one form to another. Second law of thermodynamics, which is a measurement of your disorder. How your system, you have a problem with the disorder in your system. So we can summarize it in a very simple way like this. First law of thermodynamics, it's you get what you paid for. Second law, you get less what than you paid for. And we're going to take chapters in every one of these in more details. We're going to talk about two definitions, important definition, which is microscopic and macroscopic. Macroscopic with I, this one, it means I'm looking for details. Macroscopic with A, I'm talking about global. Here, I, individual. For example, School of Engineering. If I'm talking about all the students in School of Engineering, I'm saying they are smart, they are good, they are dedicated to their lines. I'm talking about microscopic measurements, whole of School of Engineering. But if I talk about every person, every individual, this guy is talented in math, this guy is talented in art, programming, and so on. This is called microscopic with the I. This is section 1.1 is over. In section 1.2, we talk about dimensions and units. We have 4 basic dimensions: length, mass, time, and temperature. These are the 4 basic dimensions. In 1.2, we have dimensions and units. Dimensions, we have 4 basic dimensions: length, mass, time, and temperature. For units, we have 2 schools. We have 2 languages, SI units and British units. Just 2. We are happy that only have 2. For example, for the length, we used to use for SI the meter, which is the standard length scale. So the length, time, mass, and temperature. For the SI, we used to use meter. For time, second. For mass, kilogram. For temperature, Kelvin. While for British units, we used to use feet, second, slug, and Rankine. These are the basic units, the 4 basic standard units used in any problem. Solid mechanics, fluid mechanics, thermodynamics. These are the 4 standards. A lot of derivatives come from a lot of measurements like velocity, area, volume, velocity, acceleration. So let's take some. We have, for example, we can mainly focus on SI units in this course. So let's talk about velocity, acceleration, velocity V, acceleration A, like density, a specific volume, rho, nu, force, if we have energy, we have power, pressure, pressure P small, power P capital, or sometimes W, energy E. These are the most used symbolic notation for them. Volume, if you talk about volume, for example, V, but with dash like this, capital V, volume. So in SI units, volume is meter cube, length cube. Velocity, meter per second, rate of change of distance. Acceleration, meter per second square, rate of change of velocity. Density, mass per unit length, kilogram per meter cube. Specific volume is volume per unit mass, which is meter cube per kilogram. Force, force is mass times acceleration, which is kilogram meter per second square. We have done this in our lecture. This is just a repetition. Energy is force times distance. Force times distance. Here, mass times acceleration. So force times distance is kilogram meter square per second square. Kilogram meter square second square. Power is the rate of change of energy. Energy per time. It's kilogram meter square per second cube. Power, pressure, force per unit area. It's a force per unit area, which is kilogram per meter second square. These are many, there are many tons of units. We used to use for this, for example, kilogram meter per second square, Newton. Kilogram meter square per second square, which is energy standard unit, we used to use Joule. We used to use for energy per unit time, kilogram meter square per meter square per second cube, we used to use Watt as a notation or as a simplified form. One of the scientists measured this as this and they call it Watt. So one of these is 1 watt. The same for Joule, the same for Newton, the same for the last one, which is Pascal. These are the standard units we're going to use in the whole course. We can use a little bit British units, some problems, but mainly we're going to focus in SI units. In section 1.3, we're going to talk about system. What a system is. System is quantity of a matter. It's a part of a space we are interested to study. System. System 1.3. What is system? System is a quantity of a matter. Part of a space, region of a space we are interested in to study. If you talk about compressor, fan, let's talk about fan. We are interested in this fan. So this is part of a space we are interested to study. So this is called a system. If we use this as a system, we put a dashed line around it. Let's take another color. This is called the boundary. The boundary is the outline. The boundary is outline surrounding the system. So this outline separates between the system and the surrounding. Here, we have outside here, surrounding. Everything else we are not interested in right now. Ambient, you think about ambient. This is our surrounding. So everything else. We have two types of system, open system, closed system. In our course, we're going to take a lot of problems about open system and closed system. So system can be open, can be closed. System. Open system, it means something going in, something going out. So mass can cross the boundary, the green line I plotted before, the boundary, or red line. Closed system, no mass can cross the boundary. For simplicity, if we talk about piston cylinder, like this This piston was here. So I added some force, it became here. I compressed the gas. So we call it state 1, state 2. What happened? I compressed the gas. So nothing going in, nothing going out. It is here, we have the same amount of mass. That's why we call it controlled mass system or closed system. For open system, it's not the same. It's exactly the opposite. We have system that had input, at least one input or one output. So if you have one input or one output, now we are having open system. Just one input or one output. We can be 100 input, 100 output. It's okay. We have input, we have output. At least one of these. Maybe more input, maybe more output. This is called open system. Control volume. The volume is constant. Something go in, something go out. This is called control volume. So for this problem, we have a lot of applications, like compressor, turbine, fan, pump, a lot of application. Here we have piston cylinder as application, one of the most famous problem. We have tank. Energy or heat work can be add in or out. So I can add heat for any of these problems, here or here. I can add work or take work here or there. I can add here, for example, a compressor, a fan, something to add work or take work from the system. So this system accepts to take work or remove work, take heat or remove heat. The special case of those, something called isolated. Isolated means there is no heat or work can cross the system. Open system, mass can go in and out. Closed system, no mass can go in and out. Closed system is a control mass. Open system is a control volume. So isolated is no heat can be add in or work add into or out to the system. Like this one. If I kept it for 1 hour, the heat is the same, the temperature is the same. It means no work, no heat add in or out. So this is isolated system. Special case typically happen in the closed system. Special case, isolated. No heat or work added to the system. Okay? Section 1.4, we're going to talk about properties. Property is a characteristic of a system. Properties or property. Property is any characteristic. Describes a system. Like mass, volume, energy, temperature, pressure, specific volume. Anything describe a system is a property. We have two types of properties in our class in thermodynamics. We have intensive property and we have extensive property. Intensive property with letter I, independent of the size of the system. Extensive property, dependent of the size of the system. So here, it does not, this property, it does not depend on the size of the system. While here, the extensive depends, it depends on the size. For example, temperature, pressure, density, specific volume. A lot of things here. While here, we have mass, how big your system is, how small, volume, number of mole, energy. These are many, there are many of things here can we talk about? We're going to talk about them a lot. There is a very good trick to know to convert extensive property to be an intensive property, which is like this. Before we do that, let's see how can we distinguish these two. Let's give you a cup of water, and you have pressure, temperature, density, and a lot of things, and volume and mass, and so on. This is, as you know, density always for water, let's say now approximately say 1,000 kilogram per meter cube, or specific volume 0.001 meter cube per kilogram. If I divide this by 2, I make this 2 cups. So the mass is divided by 2, and the volume divided by 2. But the density here is still 1,000, the density here is still 1,000. Because the density does not change, it does not depend on the size, this means this is an intensive property. It does not depend on the size. Temperature, same pressure here, the same pressure here as here. Temperature here is here as here. But the volume here, let's say it was 1 meter cube. Here is 0.5 meter cube. Here is 0.5 meter cube. That means this is an extensive property. The mass here, 1,000 kilogram. Here is 500 kilogram, 500 kilogram. It means it's an extensive property. It depends on the size of the thing. Remember, I, intensive, it's independent of the size of the system. Independent of the size of the system. We have a very beautiful trick that we can convert this guy to this guy. Both are important. Both are needed for a problem. This is general. If you have prototype, if you have a model, if you have anything you want to study, this is very general. But if you want to go to details, how much total energy you can get, how much mass, how much volume, big volume, you need to go back to extensive. There is a way to convert from extensive to intensive by divide by mass. If you divide by mass, we call it specific. For example, a specific volume, divide volume by mass, it will be always constant, intensive property. Number of mole by mass, it will be a specific mole, number of mole. It will be an intensive property. If you divide energy by mass, a specific energy, kinetic energy by mass, specific kinetic energy, potential energy by mass, specific potential energy. So specific, for example, volume, it means volume always by mass. Specific energy, energy by mass. Specific number of mole by mass. This will be from now on an intensive property. Conversion from extensive to be an intensive. For example, a specific volume, we use like nu, it's 0.001 meter cube per kilogram for water. This number, one of the most famous number in our life, in our thermodynamic class. We'll see it a lot of time. Whenever you see this number, you know, this is 1,000 kilogram per meter cube for water at standard temperature and pressure. 1 atmosphere and 25 Celsius. We can go back from here to there by multiply by mass. Go back to the original value. So if you have a specific volume, multiply by mass, go back to be an extensive property, volume. If you have a specific energy, multiply by mass, go back to be an extensive property, energy or total energy. So we discussed already 1.5, which is specific volume and the density. So section 1.5, simply we are saying we have density, which is mass per unit volume, a specific volume, which is volume by mass. Any specific something is a something over mass. It's per unit mass, which means it became an intensive property. This is what we did in the last lecture in June 24th. So every lecture, we're going to summarize it, concise it, like 20 minutes, 25 minutes, to give it to you, instead of repeating everything in details as what we did in 2 hours, and our Wednesday, June 24th. Okay? Have a good day.